All right, continuing on with fluid flow and fluids. Now, if you're ever going to become an engineer and you go to college, you want to become an engineer and you get into mechanical engineering, you have an entire semester on just fluids. Fluid dynamics is what it's called, and you just deal with liquids and solid or liquids and gases and the fluids and the flow of fluids through turbines and compressors and you work with everything in regards to the idea of fluids. We just sort of touched base here a little bit with respect to it. As we talked about yesterday, force is equal to our pressure is equal to force divided by area, which is in a Newton per meter squared. Pascal's principle. Yesterday we talked about Archimedes. Today we're going to talk about Pascal. Okay, pressure applied to a fluid in a container is transmitted equally to every point in the fluid and the walls of the container. This is how hydraulics work. This is Blaise Pascal. He was a French scientist, philosopher, and mathematician. As a child, he was tutored by his father, who first avoided teaching mathematics to Pascal for the fear that he might overstrain his young mind. But Pascal was curious to know what geometry was all about and taught it to himself. He proved to be a math prodigy, and at the age of 16, age 16, all right? I know what I was doing at age 16. I wasn't discovering mathematical properties. Discovered one of the basic theorems of projective geometry. At age 18, he invented the first mechanical adding machine. Okay, the advent of adding machines, which is the advent before the calculators, you had an adding machine. You hit these numbers and you hit times this number and you hit another numbers and it would roll up as an adding machine. Working with his friend Fermat, Pascal formulated the modern theory of probability and combinational analysis. The probability theory arose from an attempt to deal mathematically with the gambling problems. While working on this, Pascal investigated and wrote extensively on the number system, and that we now know what is called Pascal's triangle. Pascal's triangle is a triangular array of numbers that dates back to ancient China. Over the centuries, mathematicians have discovered in the triangle many different number patterns related to situations, arithmetic, algebraic, geometry, and other branches of mathematics. It is frequently used to determine probabilities and solve problems involving permutations and combinations. That was mathematically what he did. Okay. He also dealt with things scientifically. The advent of hydraulics can be related to this right here. Hydraulic, when your brakes are a part of a hydraulic system. Okay. When you stop your car, it is not like Fred Flintstone and you put your feet down on the ground and stop the car that way. Okay. You just hit the brake pedal and magically the car starts to slow down and stop. Well, when you hit the brake pedal, you're doing absolutely nothing. You are not physically in contact with the tires. You have no contact with the tires. But when you hit the brake pedal, it compresses down and it pushes a fluid through a tube, and through that tube, what it will do is your brake pads that are near your tires, it will compress your brake pads and the brakes onto your tires and slow your tires down. That is what we're talking about here. You have a pressure that's being pushed. You pushing down on the brake pedal is pushing a fluid that allow your brakes to work and slow your car down. If you don't have enough brake fluid there, or if the brake hose breaks and you lose all the fluids that's in that hose, okay, you'll hit your brake and you won't stop. You'll just keep going on. So Pascal's idea, you utilize Pascal's idea every time you drive your car. You have a fluid in a closed container is transmitted equally. A pressure that you put on the fluid is transported to every point of the fluid to the walls and to the walls of the container. Pressure exerted on a fluid will travel undiminished through the fluid. Force may change, but the pressure will remain the constant. Pressure will remain constant. Force may change. Pressure will remain constant. This pressure that you have will remain constant as you push. Now, mind you, once again, pressure is force divided by area. Pressure is calculated by force divided by area. Now, if we take a look at a cylinder here, a tube, a pipe system here, a hydraulic idea. If I put a pressure down, I push down on this plunger here. I push down this plunger, I compress the liquid, and I put pressure on the liquid. Once again, pressure is equal to force divided by area. So if I apply a force down on this plunger, I'm pushing down the plunger, you have a fluid that's through here. Okay, we have all this fluid that's in here. You have this fluid here. I push down on it, and I have this area that is here, and I apply a pressure. This pressure here, when I start to make my area smaller, is exactly equal, though, to the pressure that is here, that is equal to my pressure here. So my pressure at 1 is equal to my pressure at 2, which is equal to my pressure at 3. My areas, though, are decreasing. So my area here at 1 is greater than my area at 2, which is greater than my area at 3. So what I have here is I have my area decreasing. But the pressure at each one of these points, no matter whether if I have a pressure gauge that's here, a pressure gauge that's here, the pressure is going to be the same throughout the entire tube center here. If A1 is greater than A2, which is greater than A3, let's take a look what happens. Force 1 is going to be greater than the force at 2, which is going to be greater than my force at 3. because once again, pressure is equal to force divided by area. So I have force divided by force at 1 divided by area at 1 has to equal my force at 2 divided by my area at 2, which has to equal my force at 3 divided by my area at 3. All these pressures must still be the same. I think I have that backwards. I'm good. My A1 is greater than the A2. Okay, this area here is greater than this area here. But when I take my force and divide it by this area, I still have to equal the same. And this force divided by this area has to be the same. And this force divided by this area has to be the same. So each one of these gets smaller as I go along. Okay, if each one of these gets smaller as I go along, but I have to be able to divide that into another number here, well, if this increases, this has to increase. If this increases, this has to increase. It keeps me, if you want to think about equivalent fractions, the idea of equivalent fractions, if I divide this by a value, I must divide the top by the exact same value. So you think of it as equivalent fractions here. So as A1 is bigger than A2, is bigger than A3, that means my force at 1 is going to be bigger than my force at 2, which is going to be bigger than my force at 3. Now my pressures are all going to be the same though. When we talk about fluid flow, we can have different types of fluid flow. We have laminar flow, which is like a smooth flowing fluid. You have nice smooth walls, you have nice tapered walls. If it's a nice smooth flowing fluid, this is called a laminar flow. We can also have what is called a turbulent flow, which is a rough flowing fluid. This would create a laminar flow because the fluid would slowly and smoothly flow through the tubes. But if I took my fluid flow and put a barrier in there and just shrink it down this way, where you have sharp edges. If we take a look at the water here or any type of fluid that's going through here, it's going to go in a straight line until you have a counter, something that's going to block it. So this water will want to try to continue to flow right through the pipe. But you have this water here, or whatever the fluid is going to hit right here, and it's going to hit right here. When it hits something, it's going to be like a ping pong or a rubber ball. It's going to bounce backwards. So it's going to hit the wall, and then it's going to want to come backwards. Well, when it hits the wall and comes backwards, you start getting some what is called turbulence. And that turbulence will cause what is called eddies. They are swirls of fluid that are formed in the turbulent flow. Swirls of fluid that are formed in turbulent flow. So if we take a look at water molecules in turbulent flow, they're going to come and they're going to hit this wall and they're going to want to bounce backwards. But if they're bouncing backwards, you still have water that's going this way that's coming right on top of it. So if they bounce backwards, what's going to start happening is you're going to start getting swirls of water here that's going to start interrupting and impeding into there. So you get these swirls of water that's going to cause our flow to be very turbulent at that point. If you've been canoeing before, you have parts of the river where it's sort of like coasting down the river on a lake. You just a nice smooth flow. That's a laminar flow. But you also have times where you have rapids, which we enjoy. Okay, which is swirls of water. Well, what is happening is you have rocks that are underneath the river. And water's going to come along and it's going to hit that rock. When it hits that rock, it's going to start bouncing upwards. And it's trying to get around the rock. Well, when it starts bouncing upward, it's going to push all the other rocks around, and you start getting what is called that turbulent flow. Okay, you start getting eddies that are there. Okay, when you start getting eddies that are there, you get rapids, and we start enjoying that. Sort of boring if you're just going down a nice river there and just coasting down. So when you deal with the idea of rapids, on a river, that's your turbulent flow also. Because what's happening is water's hitting the rocks underneath the water and spinning up and around. You have an ideal fluid? So like an ideal gas, you have an ideal fluid. A fluid that has no internal friction or viscosity and is incompressible. You cannot compress it down. Even though, and this is sometimes tough to comprehend because we always feel friction as things that warm up and you heat, and you get friction there between your hands when you rub them together. Well, water molecules, when they run into each other, they also have friction. You have friction there. Okay? You have water that heats up a little bit with respect to the friction because you have molecules running into molecules. You get friction there. Ideal fluid, there's no friction that exists between the water molecules as they interact. And it's like the same with an ideal gas law. Gas is a fluid. Even though an ideal fluid does not exist, using an ideal fluid model helps us explain real fluid properties. It's not going to be perfect. Very similar to the idea that the orbits around the sun are not circular, but we use the idea of circular because it gives us a good ballpark calculation. We've dealt with friction already. We haven't talked about the word viscosity. When we talk about viscosity, it's the amount of internal friction between molecules of a liquid. The amount of internal friction between molecules of a liquid. High viscosity means you have high friction between the molecules. It's slow flowing. It is like molasses. It is like syrup. It's like new motor oil. It will flow, but if you look at syrup, you look at molasses, it will slow, but it will be very slow moving. It will flow, but slow moving. Low viscosity you have low amount of friction between the molecules. It's faster moving. Water would be an example of low viscosity. It flows pretty easily. And once again, low viscosity, no viscosity, that's ideal, but you're not going to have it. This is your ideal fluid. If you have no viscosity, you have no viscous, there's no viscous fluids. There's no non-viscous fluids that exist. That's your ideal fluid. And this is the same thing we did up top here. When you have fluid flow here, when you have sharp edges, you're going to get turbulent. These water molecules are going to come here, they're going to come here, and they're going to hit here. And once they hit here, they're going to bounce backwards, and you're going to start getting these eddies because they'll start running into other molecules before they start flowing in there. So you're going to get turbulent. Then we have laminar. Where the water molecules are not going to run into any barriers at all. They're just going to nice and smoothly combine together. And you don't get any eddies there. You don't get any turbulence that is there. Standard atmospheric pressure. Okay, you talk about pressure. We have an atmosphere that applies pressure to us. Okay, we don't feel it, but there is pressure that's put on us from the atmosphere. If that pressure did not exist from the atmosphere, what would happen to you if you went into space? Or what would happen to you? Well, you would expand and you would eventually blow up. Okay? Because there'd be no pressure pushing you together and holding you. Yes, your skin holds you there, holds you together, but you also have pressure that continues to push on your skin that keeps you compact. If you would go into a vacuum and there would be no pressure in that vacuum, what would happen is, boom, you would make a mess. Okay, you would have blood and guts everywhere. Would not be pretty. Well, a barometer is an instrument that measures standard atmospheric pressure. Okay, a barometer measures that standard atmosphere or that atmospheric pressure. What do we have that's pushing on us? There's different ways of being able to deal with pressure at sea level. Okay, pressure at sea level is 1 atmosphere of pressure. 1 atmosphere of pressure is 1.01 times 10 to the 5th pascals, or 101 kilopascals. We have, because we're in America, we feel the English way of doing things is still the best way. It is still measured in 29.92 inches of mercury. Now, what that means is, if we take a look, you have this atmospheric pressure that is pushing down on this mercury. Okay, you have pressure that's pushing down on this mercury. This is how they used to measure it. They have this tube that they filled up with mercury and then turned it upside down. Put their finger on the end of it and turned it upside down in a vat of mercury. And they measured the level where the mercury stops. It would start falling some, but it would stop at a certain spot, because what is happening here is you have this atmosphere that's pushing down. It's pushing down and then pushing the fluid back up and supporting the fluid that is there. The max, or at standard atmospheric pressure, it will support a column of 29.92 inches of mercury. So you're looking at a column that's this tall from the floor up to here. Okay, that's how much height would be in that tube or that little cylinder that you have there. When you have a high pressure system that comes overhead, you have sunny weather. Okay, the sunny weather. Well, it's called a high pressure system that comes overhead. When you start getting a bunch of blue skies and sunny weather there, the clouds are gone. That means there's more pressure being put on you, which means there's more pressure that's being pushed here. What will happen is this will rise up to 30 inches or 30.2 inches of mercury. When you have a low pressure system, that's when you have major snowstorms, hurricanes that come through. Okay, they reach down to 28 inches of mercury sometimes. They say, whether it's true or not, but they say sometimes when you have low pressure systems come in, more babies are born, because there's less pressure of resistance for babies to being born. That's why if you have snowstorms and major snowstorms, you might have more babies born because there's less pressure put on and as a resistance. When you have sunny weather, it's high pressure, okay, not as many babies are born because there's more pressure being put on the birthing system. You have, this is more viscous. This converted into water would be 10 feet of water. 10 feet of water. So if you want to feel what happens when you have 1 atmosphere, and you want to feel what 29 or 10.9 feet of water feels like and 1 atmosphere feels like, well, right now we're feeling 1 atmosphere of pressure. It doesn't seem anything different. But if you want to change this to 2 atmospheres of pressure, you jump in the pool and you dive 10 feet down, almost 11 feet down into the pool. When you dive 11 feet down in the pool, you feel pressure of about 11 feet of water. Okay, that additional pressure that you feel on your brain and on your eardrums is what 1 atmosphere of pressure feels like. Because the pool is already experiencing 1 atmosphere of pressure. You have a pool. You have a pool with a water that is sitting there. The water doesn't hop out of the pool. So you have 1 atmosphere of pressure already on the pool. Because if this pool, if this water, that pressure wasn't there, the water would hop out. If you would go 10.9 feet to the bottom of this pool, what you will feel at 10.9 feet is 2 atmospheres of pressure. Because you have the 1 atmosphere up here already, plus 10.9 feet of water, that's going to give you a second atmosphere of pressure being pushed onto you. Typical automobile tire, 39, we have 36 pounds of pressure that's inside of that. That would be about 3 atmospheres, or 3 times 10 to the 5th pascals, which is about 3 atmospheres of pressure that you have, which is about 36 pound psi's, the pressure that you feel there. So like I said, if you want to feel what 1 atmosphere of pressure feels like, okay, we know what 1 atmosphere of pressure feels like. We feel it right now. We don't feel anything different. The atmosphere doesn't really feel different to us because our body, and this is what we're just used to. If you want to go down 10 feet, 11 feet into a pool, once again, that's an additional atmosphere of pressure being added to you. And once again, you'll feel it in your head. You'll feel the pressure there. Every 11 feet you go down, you have an additional pressure added to you. If you go deep sea diving, people that are deep sea diving, they have to put on a pressurized suit. Okay? The reason why is they have to, because if you go too far, we can handle 10 feet or 11 feet. But you go down another 11 feet, you're really going to start feeling it. You'll feel it in your ears, in your head, your eardrums may bust because the pressure is going to be hard. If you go down 40 feet or 50 feet or 60 feet in the water, that's a lot of pressure that's being put on your body and put on your head. You have to put a pressurized suit. That relieves the pressure that you have that's being put on you. So that's ways for divers, deep sea divers, to be able to eliminate problems that you have if you're deep sea diving. They put on pressurized suits. All right, questions? QED has done. We have one more day of stuff tomorrow. I'll try to get some sort of evaluation by Friday for us, but we have one more day of information. I don't know what the evaluation will look like on Friday. Sort of going back and forth on this, so I'll figure something out.